We're starting off here with the review of balancing. Thank you. We're starting with the review of balancing an equation. And this is a sample problem like you might see on your exam. I'm going to try to throw those in as the do nows, so we work an exam review kind of along the way. We're asked about the coefficient to place in front of the oxygen. So that's the only thing that's left to be balanced here. So I'm not going to worry about looking at all the other elements. We're just going to focus on the oxygen. So I'm going to make my little chart and only focus on oxygen because it's the only thing left to balance. On the reactant side, we've got 2. That's what that little subscript there means. On the product side, there are 2 compounds that have oxygen. It's the carbon dioxide and the water. So we've got 5 times 2 plus 4 times 1. That's from the carbon dioxide. There's 10. From the water, there's 4. That means 14 oxygens are on the product side. The lowest common denominator between these two is 14. So we're going to multiply that by 7. And that gives us the answer of B. So how do we do with that one? That's a sample from straight from the test bank. How do we do? How do we do with this one, guys? Good. All right. Then let's finish up chapter 7. Chapter 7 is a pretty big chapter. Hopefully you had a chance to look at the videos for chapter 7. I'm going to go on the assumption that you did have a chance to look at it. And we're going to focus mainly on doing practice problems, which I think is the most helpful. The first section that we're starting with is section 7.7, and that's on mole relationships in chemical equations. The reason why we can do all of these calculations is because of the law of conservation of mass. In a regular old chemical reaction, matter can't be created or destroyed. So the amount of matter that you start with as reactants equals the same amount of products. So there's no change in the total mass. So if the mass of my reactants was equal to 50 grams, then the mass of my products also has to be 50 grams. Because of this, we can do calculations to predict how much product we form. When you're reading a chemical equation, the coefficients, which are the numbers in front, they can be read like the number of moles of a substance. So we can read this equation as 2 moles of iron plus 3 moles of sulfur yields 1 mole of this iron sulfide compound. Using this information, we can write mole-mole factors that will tell us about the relationships between the different substances in the equation. A mole-mole factor is just a ratio, and you get the information directly from the chemical equation. So I'll write some out, and then I want you guys to try writing some out too. So I like to do this kind of color-coded. The first one we'll do iron in red. The sulfur, I wish I could do yellow because it's kind of a yellowish color, but that's not going to show up very well. So the sulfur will be green, and then purple will be for the iron 3 sulfide. The first mole-mole factor that I'm going to write is going to be the relationship between iron and sulfur. There are 2 moles of iron, and I abbreviate mole, M-O-L. For every 3 moles of sulfur. And just like with the conversion factors that we were doing in chapter 2, these mole-mole factors, you write one, and the second one is the reciprocal. So this time we'll put the moles of sulfur on top. And the 2 moles of iron on the bottom. Those are the mole-mole factors for iron and sulfur. Now let's try the mole-mole factor between sulfur and iron 2 or iron 3 sulfide. How many moles of sulfur am I putting in the top of this mole-mole factor? We're just reading how many moles of sulfur we have from the equation. Yeah, we've got 3 moles of sulfur. How many moles of iron 3 chloride do we have in the equation? Oh, that's iron. We want the product, which is iron 3 sulfide. So that's a mole-mole factor that describes the relationship between these 2 compounds. If you have 3 moles of sulfur, you'll produce 1 mole of iron 3 sulfide. The other way we can represent that is if you make 1 mole of iron 3 sulfide, that means that you started with 3 moles of sulfur. I want to take a minute and I want you guys to try writing out the last set of mole-mole factors. So the relationship between iron and the iron 3 sulfide. There should be 2 mole-mole factors. You don't have to write it in the chat. It's not exactly easy to do. If you feel like you want to, go for it. But I'll give you a minute while I'm setting up to maybe jot it down in your notebook, or at least think about it. Yeah, 2 moles of iron for every 1 mole of iron 2 sulfide. We're literally just reading the numbers from the chemical equation and putting them in fraction form. And once you do that for 1, then you just write the reciprocal. We need to write these mole-mole factors because we're going to use them in calculations. It'll help us figure out if I have this many moles of iron, let's say, how many moles of iron 3 sulfide can I make? So how are we with mole-mole factors? We're going to be practicing writing these pretty much for the rest of our time. So if we're good to move on and just kind of practice, let me know. Otherwise, we can stay here for a second. Then let's do a quick learning check. You've got this equation. We're making some ammonia gas. Choose the mole-mole factor for hydrogen gas and nitrogen gas. I'll give you a minute or so to look it over, and then you can chime in with your answer in the chat if you so choose. But in about a minute, I'll go over it. All right. Mole-mole factor for hydrogen gas and nitrogen gas. Here's hydrogen gas, nitrogen gas. Whenever you don't see a coefficient, remember that that means 1. So we need a mole-mole factor that has 3 moles of hydrogen and 1 mole of nitrogen. The only one that fits the bill is letter B. So let me know, are we good? Do we want to do another practice problem? Let me know what you're thinking. Yeah, we can do another one. So I want you to write a mole-mole factor for nitrogen gas and ammonia. I'll give you another minute, and then I'll check in and write one. All right, it looks like we have one answer in the chat. 1 mole of nitrogen gas for every 2 moles of ammonia. And that is absolutely correct. The other one that you could have would be the 2 moles of ammonia on top and the 1 mole of nitrogen gas on the bottom. So let's move on and start using these. So I'll show you a sample of how we can use the mole-mole factors. How many moles of iron 3 oxide can form from 6 moles of oxygen gas? Our given information is 6 moles of oxygen gas. So I'll highlight that in yellow in the equation too. What we're asked about is the moles of the iron oxide compound. To rephrase the question, I'm starting with 6 moles of oxygen. How many moles of iron 3 oxide are formed? So that's how I rewrite the question. We are on the ball today, but I'm going to keep going through so we can see how to get there. To get from the moles of oxygen to the moles of iron 3 oxide, we have to write a mole-mole factor. So that's how we're going to set up our equation. We're starting with the 6 moles of oxygen. We have some kind of mole-mole factor, and we'll use that to get to an answer. Until you're comfortable, I suggest writing out both of the factors and then choosing whichever one is right to fit the equation. To write the mole-mole factors, remember that we look at the chemical equation for the coefficients. And we literally write out what those numbers are and just say 3 moles of oxygen instead of just the number 3. And we have 3 moles of oxygen for every 2 moles of iron 3 oxide. The other possibility is the reciprocal. Which one of these should we use? A or B? We should use B. So B has the moles of oxygen in the denominator. And that's what we need to cancel out the moles of oxygen in the top. And someone has their microphone on. You hear a lot of noise in the background. So check your settings. Okay. When we have the oxygen in the bottom, we can cancel out moles of oxygen, and we're left with moles of iron 3 oxide. And that's what we want to end up with. When you look back at how you rephrase the question, that's what we're trying to find. When you put this into your calculator, you're going to do 6 times 2 divided by 3. And that's 12 divided by 3, which gives you 4. Let me write that in black. That's still not black. So in the problem, we have 6.0 moles. So we should write our answer with 2 sig figs, 4.0. Do we want to go on and do another one? So here's another one. This time, we need to figure out how many moles of iron we need to react with 12 moles of oxygen. If you are very much into colors, like I am, you'll definitely want to try kind of until you get it. Use the colors to help you. Okay, I'm asked about the moles of iron, so let me look at the iron, in the equation. And then we have the oxygen here. So I'll give you a minute. Try to work through it. Start by writing out the mole factors and choosing which one you'll need. And if you can get all the way through and get to an answer, throw it in the chat. But I'll give you about a minute or so, which is not a whole lot of time. I understand. But you'll at least see, maybe I don't understand this as well as I thought. And then we can work it out together. If you're still working, that's okay. First thing we're going to do is write our mole factors. We're looking at the relationship between iron and oxygen gas. In our chemical equation, we see 4 moles of iron and 3 moles of oxygen gas. That's our first mole factor. The second one is just the reciprocal. So you flip it upside down. Put the 3 moles of oxygen on top and the 4 moles of iron on the bottom. Then we start to set up the equation. We're starting with 12.0 moles of oxygen gas. We need to choose which one of these will actually get us to number of moles of iron. So let me know which one we use. Is it A or is it B? We need the oxygen in the bottom so it cancels out with the oxygen that's already in the numerator. I always do the unit analysis before I touch my calculator. So I make sure that all of my units cancel and I end up with the unit that I want at the end. That's going to become very important when we move on to doing more complicated calculations. In your calculator, you're entering 12 times 4, and then you're dividing that by 3. So 12 times 4 is 48. 48 divided by 3 is 16. So our answer is C. Questions here? Good. Where we're going next, this is the crux, writing that mole factor. There's some other extra stuff that we need to do too, but this is the key to solving the stoichiometry problems that we're going to be solving coming up. So now we're going to be doing mass calculations. We're going to take what we learned about the mole factors and then bring in the concept of molar mass. This is the kind of generic way of going from the mass of substance A to the mass of substance B. I put it in here because some people are kind of visual creatures in terms of having a generic formula. I prefer to work through a problem. So if you like this was in the pre-recorded lecture. It's in the live slides as well. If you like that when you're doing your problems, sky's the limit. I, however, would not be able to do well with just the slide. I'm going to be honest. I need to see a problem worked out. I need the colors, all the things. So if you have color pencils, highlighters, markers, crayons, whatever it is, finger paint, do what you do to help, one, make it colorful and happy, and two, the colors really help to solidify, what goes where and why. I'll walk through this example and then we'll do some more to practice. We're going to be building on this problem type. Suppose we wanted to determine the mass in grams of ammonia that can be produced from 32 grams of nitrogen in the following equation. How in the world would we do that? Well, let's start by figuring out what our given information is. Didn't mean to do that. Meant to go to the colors. Let's figure out what our given information is and then see what gaps we have that we can fill in with our knowledge and get from where we are to where we've got to go. Currently, what we know is that we have 32 grams of nitrogen gas. And we're trying to figure out the mass in grams that we'll make of ammonia. So that's our question. To get from the mass of nitrogen to the mass of ammonia, we have to use moles. So here's where we're going to get colorful again. I'll use the green for nitrogen. I'll use blue for ammonia. This is our plan. To go from grams of nitrogen to moles of nitrogen, we have to use the molar mass. We talked about molar mass last time. I'll remind you of what that is. Molar mass, we're just looking at the atomic mass on the periodic table for all of the elements in the compound. We're adding those together and saying that that is the number of grams in 1 mole of substance. So in the case of nitrogen, when you look up nitrogen, it'll say 14.01, or if you're using the other periodic table I've posted, it'll say 14.007. Some periodic tables have a few more digits than others. Whichever way you go, you'll still get to the right answer. In this case, the molar mass of nitrogen is going to be equal to about 28. So it's, when I work these out, which I usually do work them out ahead of time just to make sure there's no issues with the problems, I used 14.007. So the molar mass that I'm going to use in this problem is 28.014 grams. To go from the moles of nitrogen to moles of ammonia, we have to use our mole-mole factor. Then we use the molar mass of ammonia to get to grams. That's the plan. The molar mass of ammonia, by the way, you take the 14.007 and add to that 1.01 times 2. And you get about 17 grams. Is everybody with me so far? I hope it's a yes. Let's start filling in the numbers here. The grams of nitrogen gas, we have 32. That was our given information, right? Now we need to use the molar mass as a conversion factor. We've got A, we've got B. Which one of these should I use if I'm trying to convert from grams to moles of nitrogen gas? So that's the first part. Now we need to write a mole-mole factor that's going to take the moles of nitrogen and convert that to moles of ammonia. If we want the moles of nitrogen to cancel, the moles of nitrogen need to go on the bottom. And this is where we go to our equation, the chemical equation. How many moles of nitrogen gas do you see in the equation up here? We're looking up here. How many moles of nitrogen gas? There's only one. Remember, we're looking at the coefficient here. So yeah, when there's no number in front, then you use 1. What about the ammonia? How many moles of ammonia are there in the chemical equation? 2. That's our mole-mole factor. And the form that it's always going to take in here is whatever it is that we need over what we have, or the given information. Let me write given. I like the way that sounds better. So we were given the amount of nitrogen gas. That goes, when we make our mole-mole factor, the number of moles of nitrogen from the chemical equation goes in the bottom. What we need to answer the question is the number of grams of ammonia. So the moles of ammonia from the chemical equation are going to go into the top of our mole-mole factor. And we're going to practice that. The last piece is another molar mass conversion factor. Which one do we need to use if we're trying to convert from moles of ammonia to grams of ammonia? Not this time. This time we're going to go for A, because we need grams at the end. So we're going to cancel out the moles to be left with grams at the top. Participation is much appreciated. So we'll look at our plan to see if we did what we needed to do. We're starting with grams of nitrogen gas. Those units cancel, and now we're at moles of nitrogen gas. That's what we wanted to do for the first step. The second step, we're using our mole-mole factor to figure out the moles of ammonia. We're canceling out the moles of nitrogen gas, and we're left with moles of ammonia. The last piece is using the molar mass as a conversion factor to take moles and turn it into grams of ammonia. So all of our units cancel. We have the right units at the end. We can go ahead and use our calculator. What we do here is 32 divided by the molar mass of the nitrogen gas multiplied by 2. We're technically dividing by 1 here, but it's not going to change the number. And then you're multiplying by 17.031, which is the molar mass of the ammonia. When you put all that craziness into your calculator and you account for sig figs, which you should only have 2, you get 39 grams of ammonia. I want you to take a second, try it out in your calculator, and make sure that you end up with the same answer that I do. If you do, then we're ready to move on. If you don't, make sure that you figure out where you went wrong. Because getting to the equation is one thing, entering it into your calculator is another. So I'll give you another maybe 30 seconds or so to try it out and make sure that you end up where I did. How we doing? We ready to go on and chew another one? So let me know. Do you want a few minutes to try this one on your own? Or do you want me to kind of help you set it up and then I give you a minute? Okay. Yeah, if you want to work on it, just ignore me. Mute. Do your thing. But if you want help setting it up, then I'll help you set it up a little bit. We're looking at grams of oxygen as what we need. And we're starting with the amount of product that we made. So our question is, if we have 45.8 grams of iron 3 oxide, how many grams of oxygen gas were needed? So we're going to start with the grams of iron 2 or iron 3 oxide and convert that to moles. Then we're going to take that and convert it to moles of oxygen, and finally to grams. You'll need the molar mass of iron 3 oxide. Then you'll need a mole-mole factor. Then you'll need the molar mass of oxygen. That's oxygen gas, which is O2. So don't forget that when you're setting up what the molar mass is. I'll give you until 3:05 to get as far as you can on the problem, and then I'll come in and start solving. So the way you figure out the molar mass is you use the periodic table. So let's say for iron 3 oxide, you look up the atomic mass of iron, you look up the mass for oxygen. There are 2 iron atoms and 3 oxygen atoms. So you would take 2 times the mass of the iron and add that to 3 times the mass of the oxygen. Does that help, Brandy? You're welcome. Okay. I'm going to go to the next slide to give myself a little bit more room because I can't write everything on this slide. Okay. So we need some bits and pieces here. The molar mass of iron 3 oxide I found that to be 159.70 grams. And yours may not be exactly what mine is, depending on what periodic table you use. But they should be very, very similar. The molar mass of oxygen, the gas, remember that there's 2 oxygen atoms in oxygen gas. So that is going to be 32 grams. Now we can start setting up the problem. For the first step, we need to take the grams of iron 3 oxide and convert that to moles. To do that, we need the molar mass. If I want to cancel out grams, that means I need to put the molar mass in grams on the bottom. And 1 mole at the top. So that is my molar mass conversion factor. Then I have to write a mole-mole factor. And that's going to get me to the moles of oxygen. Remember that for the mole-mole factor, we're going to look at the compound that we're given information for, in this case that's the iron 3 oxide, then we look at the chemical equation and write how many moles of that we see. That goes in the bottom. What we need to figure out is the oxygen gas. We go to the chemical equation and write how many moles of that we see. That's our mole-mole factor. The last piece is to convert the moles of oxygen to grams of oxygen. Again, we're going to be using molar mass, but this time we're canceling out the moles of oxygen gas. So that has to go in the bottom. And in the top, we need the grams of oxygen. And that should get us where we want to go. If you didn't get here, take the time and try to put it into your calculator and see what you get. I'll show you how all the units cancel. We cancel out the grams of iron 3 oxide. And that leaves us with moles. That was the first thing we wanted to do. Then we use the mole-mole factor to get rid of moles of iron 3 oxide and trade that for moles of oxygen gas. The question is asking for grams, so we need to use the molar mass of oxygen gas. And that gets us to grams. When you put all that into your calculator, you should get 13.8 grams of oxygen gas. And just so that you know how to get there if you didn't get there, for your calculator, you're starting with 45.8. Dividing by 159.70, multiplying by 3, dividing by 2. So when there's a number in both the numerator and the denominator, you can't ignore it. The last step is multiplying by 32. If you wanted to put all of this in together, you may want to use parentheses. Depending on the calculator, you may or may not need to. So talk to me about this one. How did it go? Is it starting to sink in a little bit more? Is it struggle? Let me know. Good. Good. It takes time and practice with these problems. So let's do one more. This time, I'm going to give you 5 minutes cold to try setting it up. Get as far as you can. Then I'll go through and solve it. So 5 minutes, work on this. If your brain feels like it's going to explode, you could also say, you know what, I'm going to take a 5-minute break right now. Shake out your brain, get some water, take a lap around your room, whatever you got to do. If you can work on this, work on it. If you need a minute, take 5. but this will be kind of our pseudo break. Either way, I'll come back in 5 minutes and start solving. If you have questions in the meantime, go ahead and ask or write it in the chat though. I'll start writing out the question and setting up the problem. We've got 13.1 grams of water. We need to know how many grams of oxygen gas reacted. So we're taking 13.1 grams of water. And we have question mark grams of oxygen gas. There's our given. That's what we need, the oxygen gas. With these problems, you always need the molar mass. Remember that for diatomic molecules like oxygen gas, hydrogen gas, you need to take the atomic mass that you see on the periodic table and multiply it by 2. As for our plan, we're starting with the grams of water. We need to get to moles of water using the molar mass of water. Then we convert the moles of, oops, I left my oxygen out of the water. That's not water anymore. There we go. We take the moles of water and convert to moles of oxygen gas. That's using our mole-mole factor. Then we take those moles of oxygen gas and convert them to grams. You need the molar mass of oxygen to do that. Starting with what we're given, which is the 13.1 grams of hydrogen of water, we need to have 3 bridges to get from where we are to where we want to be. First bridge, we're converting grams to moles. If we want the grams of water to cancel, we've got to put the molar mass with the grams on the bottom. Moles of water goes in the top. And that's just the definition of molar mass. 1 mole of water is equal to 18.02 grams of water. Then we write the mole-mole factor. And remember that that is what we need over what we're given. What we need to figure out is about oxygen. So we look for oxygen gas. There's 1 mole of it. Remember, when there's no coefficient, you use 1. What we're given information about is the water. So we look at that coefficient and it's 2. That goes in the bottom. The next part, we have to take those moles of oxygen and convert to grams. This time, the grams are going to go in the top and the moles on the bottom, because the moles of oxygen gas will cancel out, leaving you with grams of oxygen gas. Always go through and check to make sure that your units cancel. You need the unit in the numerator and the denominator to cancel out the unit. So first we get rid of the grams of water and we get to moles of water. We go from moles of water to moles of oxygen gas using the mole-mole factor. Then we finally convert to grams of oxygen using the molar mass. All that checks out. In your calculator, 13.1 divided by 18.02 times 1 divided by 2 times 32. With sig figs, which we need 3 of them, you should get 11.6 grams of oxygen gas. So how was that one? Did that feel a little bit better than the last ones that we did? Do you feel like you're improving? Talk to me about how you feel and what you need. That's always good to see. We're going to keep doing this problem type. We're just going to build on it. So if you still have some question marks, there's plenty of opportunity to do practice and continue learning. Now we're moving on to limiting reactants and percent yield. They have this whole peanut butter sandwich analogy. If you take 2 slices of bread and 1 tablespoon of peanut butter, your peanut butter sandwich is trash. That's number 1. Number 2, you can't just have peanut butter. You got to have some jam. And not grape. I'm sorry, I'm too bougie for that. I need strawberry. So this whole example here, no. But we will talk about a limiting reactant, and then I'll give you a better example. A limiting reactant is just the chemical reaction where you have a substance being used up first. So, whichever one gets used up first limits the amount of product that you can make. That means that you also have an excess reactant, the one that doesn't complete all the way. You got some left over. Now, instead of a peanut butter and jelly sandwich or something like that, which is great in its own right, I'd prefer grilled cheese. Now, when you make a grilled cheese sandwich, you can go real basic. 2 slices of cheese, a couple slices of bread. Boom, done. When I'm making it for my kids, that's what they get. They don't appreciate the finer things of life yet. However, I'm an adult. Use some special cheeses. Smoked Gouda. Oh yeah, we do it. Mix it up. Take that, maybe a little Munster, something different. Now we're not going to do all that for the example, but a grilled cheese can be elevated to gourmet. That's all I'm going to say. But let's say we're making some grilled cheese sandwiches for some hungry children, which I do. I'm not going to say often, but it happens. Our reaction is going to be 2 slices of bread We're going to take 2 slices of cheddar. I don't do no American cheese. That stuff is plastic. You make 1 sandwich. That's our reaction. Now, of course, you need a little something to put on the outside, some butter or something to toast it up on the griddle or in the pan. But we'll ignore that for now. That's a little too complicated. What if I look around, look in the fridge, get out the bread, get out the cheese, and I find that what I have is 8 slices of bread, and 4 slices of cheese. How many sandwiches can I make with that? If I've only got 4 slices of cheese, then this is only enough for 2 sandwiches. With the bread, I've got enough for 4 sandwiches. I can't make 4 sandwiches because I've only got enough cheese for 2. So I end up making 2 sandwiches and making them share. Now they're young, so they'd share sandwiches anyway. But the idea here is there's a limiting reactant. And it's the cheese. The bread is in excess. So we figured out how many sandwiches can I make with the bread? I have enough for 4. How many sandwiches can I make with the cheese? I've got enough for 2. How many am I going to end up making? The lower amount, which is 2 sandwiches. Does that concept make sense? Because we're going to use that when it comes to a real chemical equation in figuring out a limiting reactant. So talk to me. Does this concept make sense? All right. So let's do an example. I've got 3 moles of carbon monoxide, 5 moles of hydrogen gas. I need to figure out how many moles of methanol I can make and which one of these reactants is the limiting reactant. So I like to highlight or underline the given information. Helps me focus on what I need to know. When you have a limiting reactant problem, you'll recognize it. It may say, what is the limiting reactant? That's a clue. But if it doesn't, you'll notice that you have amounts for 2 reactants, not just 1. And the other problems we were doing, you have this number of grams or this number of moles of a reactant. How much product do you make? Here, we're saying you have ingredient A and ingredient B in these amounts. How much of the product can we make? we have to essentially answer two questions then. The first question is, if I have 3 moles of carbon monoxide, how many moles of methanol can I make? And CH4O, CH3OH, they're the same thing. I just can't break my habit of writing alcohols with the OH at the end. So that's one question that we have to ask. The other question is, if I started with 5 moles of hydrogen, how many moles of methanol would I make? Well, now that we break it down like this, these are the problems we started doing at the beginning of class, where I know how many moles I have. I use a mole-mole factor to get from point A to point B, and then I know how much. So let's do that. Here's our carbon monoxide. Here's our methanol. The yellow doesn't show up super well, so I'm not going to write in it. We need to get from carbon monoxide to methanol. So that means the moles of carbon monoxide from the equation, the chemical equation, should go in the bottom of our mole-mole factor. The moles of methanol go in the top. The ratio is 1 to 1. So if we have 3 moles of carbon monoxide, we would make 3 moles of methanol. We do the same thing with the hydrogen. We write the number of moles of hydrogen from the chemical equation in the denominator of the mole-mole factor, because we're trying to cancel out moles of hydrogen. At the top, we write how many moles of methanol. So there's 1 mole of methanol produced for every 2 moles of hydrogen gas. Five divided by 2 is 2.5. We can only make the amount that the limiting reactant can make. So that's going to be the least amount of product. So that means we're going to produce 2.50 moles of methanol. And that hydrogen gas is limiting. So how are we doing so far? This is limiting reactants. Then I'm going to give you one to try for yourself. Or I lied. We're going to go straight to the harder one. which is taking the mass to mass that we were doing, mass of A getting to mass of B. And then I have another one of those for you to try. So if we're good on that one, then we're going to step it up and do this problem. Now this one, I believe I already showed in the video. I'm going to walk it through again, and then I'll let you loose and you can do your own. So we're starting out, we want to know how many grams of carbon monoxide are formed. We've got 70 grams of one reactant and 50 grams of the other. What we're doing here is, again, answering two questions. The first question, if I have 70 grams of silicon dioxide, how many grams of carbon monoxide do I make? That's one question. The second question is, if I have 50 grams of carbon, how much carbon monoxide do I make? If you feel comfortable and you want to try this one, or if you remember from the video, that's totally fine. But you can work through it while I work through it, or you could just watch. Totally up to you. Customize your experience. Remember that for these questions, we need to have the molar mass. You have to calculate that. So I'm not going to go through and calculate that here, but I will write it out above each one. So carbon, you just look at the periodic table. It's 12.01 grams is 1 mole of carbon. For the silicon dioxide, that is 60.088. And last but not least, I'm going to do the carbon dioxide in blue just because the yellow doesn't show up as well when you're writing. Carbon monoxide has a molar mass of 28.009. Armed with that information, we can get started. I'm just going to go through and write out the equation here. I'm not going to write out the plan, but I'll walk it through and go through how the units cancel. First, we're going to use that molar mass. The number of grams goes in the bottom, and the moles go in the top. Then I have to write out that mole-mole factor. What I need to figure out is how many grams of carbon monoxide. So I'm going to go to my chemical equation and look at carbon monoxide, there's 2 moles there. What I'm given is information about the silicon dioxide. There's no coefficient, so I write a 1. Last step, molar mass of carbon monoxide, so we can convert moles to grams. This time the grams go in the top and moles go in the bottom. We cancel grams, we're left with moles. We cancel moles of silicon dioxide, we're left with moles of carbon monoxide. Cancel that out, and we're left with grams. When you do all that, you get 65.3 grams of carbon monoxide. Then we have to do the same thing for the other side. Starting with the 50 grams of carbon, we first have to convert those grams of carbon to moles. Moles on top, grams on the bottom. Mole-mole factor, we're still trying to figure out how much carbon monoxide. So that still goes in the top here. But the denominator is going to change because we're looking at carbon. And there's 3 moles of carbon from the chemical equation. This last conversion factor is going to be exactly the same as the time we did it before, because we're still converting moles of carbon monoxide to grams make sure that all of our units cancel. We get to moles of carbon, the moles of carbon monoxide, and then grams of carbon monoxide. We would make 77.7 grams of carbon monoxide if we were to start with 50 grams of carbon. Which one of these is our limiting reactant? Is it the silicon dioxide or the carbon? Yes. Yes. Okay. So for that, the mole-mole factor, what we're looking at is I like to call it the need, or the need to find, and the given. That's the form that the mole-mole factor is when we're doing these types of mass-to-mass problems. So the need to find is, in the question, how many grams of carbon monoxide, right? So we need to find out something about carbon monoxide. I go to the chemical equation that is provided, and that says 2 moles. So that's what I write on top. I'm given information for the silicon dioxide and the carbon. This time we're dealing with the silicon dioxide since that's the side I'm writing on. So I go here. I look at the chemical equation. There's 1 mole. When there's no coefficient in front, you assume 1 mole. and I fill that in at the bottom. So we figured out that silicon dioxide is limiting, and we're going to make 65.3 grams of carbon monoxide. Any other questions, or are we ready to move on? I'll take that as we're ready. So I want you guys to try this one. I'll give you 5 minutes to get things set up, and then I will set everything up and walk it through. You can keep on working if you're trying out the problem. I'm just going to start writing now because it just takes me a while. And if you get stuck, you can look at what I'm doing, and that might help. So I won't explain it necessarily. I'm just going to be writing. So I've written out the molar masses of each of the compounds we're interested in and set up the 2 questions that we need to answer. So at this point, I will start explaining what I'm doing. I'm going to go through and write out the equation and kind of talk it through. I'm not going to write out the plan like I started doing. Just going to write out the equation. So the first question that we'll answer is, if we start with 2.50 grams of nitrogen gas, how much ammonia gas will we make? Step 1 is to convert those grams of nitrogen gas to moles. We always use the molar mass. For the first step, the number of grams goes in the bottom, because we're trying to cancel out with the grams on the top. We put moles of nitrogen in the top. That's just the definition here. 1 mole of nitrogen gas is equal to 28.014 grams of nitrogen gas. Then we write our mole-mole ratio, or mole-mole factor. What we need to figure out is how much ammonia. So I'm going to look at my chemical equation to see how many moles of ammonia are made. And there's 2 there. What I'm given information about is nitrogen gas. I look at the chemical equation for how much nitrogen gas is required to make those 2 moles of ammonia. I only need 1. There's my mole-mole factor. Finally, I use the molar mass of ammonia. This time I want grams at the top. I'm trying to cancel out the moles of ammonia and convert them all over to grams at the end. I'm going to set up the second problem. And if you didn't get to, writing out all these steps, then you have a chance to try the math with your calculator and see what answer you get. You can compare it to mine. So I'm going to set up the hydrogen equation now. Same idea here. We're starting with 2 grams of hydrogen gas. We're first going to use the molar mass of hydrogen gas to figure out how many moles we have. Then comes the mole-mole factor. We're still interested in making ammonia, so we look again at our chemical equation. 2 moles of ammonia. But this time, we're doing hydrogen. We're figuring out how much hydrogen we're converting to ammonia. So we look at the chemical equation for hydrogen, and there's 3 moles there. That's our mole-mole ratio. The last step of this is the same. We're converting the moles of ammonia to grams of ammonia. I'll show you that our units cancel. We first get to moles of nitrogen, then moles of ammonia, then grams of ammonia. And when you do all that math, you should get 3.04 grams of ammonia being produced. With the hydrogen, we cancel out the grams of hydrogen and we end up with moles. Cancel the moles of hydrogen, end up with moles of ammonia. And finally convert moles of ammonia to grams of ammonia. When you put all that into your calculator, you get 11.3 grams of ammonia. We're trying to figure out how much ammonia will actually be made. and that's 3.04 grams, which means that the nitrogen is limiting. So how do we feel about that? That's about as complicated as it gets when it comes to doing these mass-to-mass stoichiometry problems and the limiting reagents. Good. So you know we're not done. We got to add some more to it. So in this section, we're talking about limiting reactants and also percent yield. So let's talk about percent yield real quick. The theoretical yield, that's the maximum amount of product that you can make. That's what we've been calculating so far. So that's the mass to mass questions. If I start with this many grams of this, how many grams of that will I make? The actual yield is the amount of product you actually obtain. That's experimental data, which you're not going to do. So that'll always be provided to you. The percent yield is the ratio of these two things, the actual and theoretical yield. So this is the equation you need to know. Actual yield divided by theoretical yield times 100%. We can take this concept and combine it with the mass-to-mass question. So you can be told what the actual yield is, how much reactant you started with, and you can do the calculation to figure out the theoretical yield and use that in your calculation of the percent error or the percent yield. So that's what we're going to do next. We're on a space shuttle. Lithium hydroxide absorbs carbon dioxide and it forms lithium bicarbonate. What's the percent yield of the reaction? Oh yeah, I can go back. You're welcome. Back on the spaceship. We've got 50 grams of lithium hydroxide, and we make 72.8 grams of lithium bicarb. What we have to figure out is the percent yield. Get out my highlighter. This 72.8 grams of lithium bicarbonate, that is the actual yield. The 50 grams of lithium hydroxide, that's our given information to calculate the theoretical yield. So I'm going to work this problem through. Feel free to jump ahead of me, work it out on your own, do the theoretical yield, and then calculate the percent yield using the actual and theoretical yields. I'm going to work it through, and there'll be plenty of chances for you to kind of get unstuck and try things in your calculator if you don't feel comfortable going ahead and doing the whole thing. I will write out the molar masses because that's always helpful. So those are the molar masses. Make sure you know how to figure those out, because oftentimes you will not be given the molar mass within the problem. I'm giving them here just because we don't have a whole lot of time. First, we use the molar mass of lithium hydroxide. The grams go in the bottom, so we cancel the grams that are already in the numerator of our starting information. One mole goes in the top, because 1 mole of lithium hydroxide is equal to 23.948 grams. Next, we have our mole-mole factor. What we need to figure out is about these lithium bicarbonate. I look at the equation I'm given. I don't see a coefficient, so I'm going to use 1 here, and that goes in the top. What I'm already given information about is the lithium hydroxide. I look at the chemical equation for that. I also don't see a coefficient here, so we're going to use a 1 for that as well. The last piece is converting 2 grams of lithium bicarbonate. We put the grams at the top, and moles on the bottom. That will cancel the moles and leave us with grams. We get some moles of lithium hydroxide, then moles of lithium bicarbonate, then grams of lithium bicarbonate. When you go through and do the calculations, that's 142 grams of lithium bicarbonate. And what does that actually mean? Because we're not done yet. Normally we do this and then it's like, hooray, we did it. And it's like the Dora song, you know? I'm not going to sing it because YouTube is going to take me down. But you know what I'm talking about. This is our theoretical yield. What we need to calculate is the percent yield. This is our equation, and we just fill in the numbers. The actual yield was provided in the question. The theoretical yield is what we just calculated. When you do the math, you should get 51.3%. Not great, but that's what it is. Let me know if you have questions or if you're ready to move on. Okay. Last section of Chapter 7. We're going to talk about the energy in chemical reactions. The units, you're typically going to see the joule. Oftentimes it's going to be kilojoules. And as a reminder, that kilo means 1,000. Don't forget your prefixes. They come back. When you have these energy problems, sometimes the question will tell you something about joules, and you have to report your answer in kilojoules, or vice versa. So watch your units here. We've got two types of reactions that we're going to talk about in terms of energy. There's exothermic reactions where you release heat. So you've got your reactants, they're high in energy, they come together, bonds broken, bonds formed, and then you have products that are lower in energy. That means that heat is released. When we release heat, we write it on the product side. Just like the compounds in this chemical equation, we can write conversion factors that describe the amount of heat released and the number of moles of the different substances in this chemical equation. So I'll give you an example. If I have 1 mole of hydrogen gas, then that means I'm going to release 185 kilojoules of energy if all of that hydrogen gas reacts. And then I can write the reciprocal. I'll show you one more. If I make 2 moles of HCl, along with that, I'm going to release 185 kilojoules of energy. And I can also write the reciprocal of that. So 2 concepts here. Exothermic reaction means you're releasing heat. That's on the product side of the equation. Second concept, you can write conversion factors that relate the amount of heat in a reaction to the number of moles of each substance in the reaction. We're going to do this again for the endothermic reactions. So can I move on to the next slide? And for time's sake, I'm going to move on. Second reaction type when it comes to energy is endothermic reactions. With these reactions, you've got reactants that are lower in energy, and they have to absorb heat in order to come closer and react. Bonds broken, bonds formed, you make your products. Your products are higher in energy than your reactants. This time, when we represent our energy change, the energy is going to be on the reactant side because you have to put some energy in. You have to heat it up. Then you form your products. Notice that there's a positive sign here because we're adding it in. I didn't mention before, I'm going to go back very quickly. For exothermic reactions, that change in heat is negative. So negative and then your number. It doesn't mean that it's negative energy. It just shows whether or not you're releasing energy or you're absorbing energy. Just like before, we can write those conversion factors using the energy and the number of moles of each substance. If we wanted to relate the oxygen with the amount of energy required, if we want to react 1 mole of oxygen completely, we need 180 kilojoules of energy. And then we can write the reciprocal. This is important because we can actually calculate how much energy is released or absorbed when we know how much reactants or products we're making or how much we're starting with. So let's give that a try. How much heat in kilojoules is released when nitrogen and hydrogen react to form 50 grams of ammonia? You have to watch here. What you're told is 50 grams of ammonia. What we were writing, those conversion factors have to do with moles. So make sure that if you're given the number of grams to start with, that you convert to moles first. That's the only trick here. So our molar mass for this, and we've used this a bunch of times, but it's 17.031 grams. And we're going to set it up where first we figure out how many moles of ammonia are we starting with. For that, we need the molar mass. We put moles of ammonia in the top and the grams in the bottom. The next step is to write that conversion factor. We're saying that heat is released, so it's negative 92.2 kilojoules, but we don't really care about the sign for this, so you don't need to include it when you're doing your calculation. We can write 2 conversion factors here where we're using, and I'll use a different color here, the ammonia and our energy. If we make 2 moles of ammonia, we release 92.2 kilojoules of energy. And then we can write the reciprocal. We're trying to get rid of the moles of ammonia, so that needs to go on the bottom. And the energy will go at the top. We get rid of our grams. We've got moles. We get rid of our moles. We've got energy. And to write out the plan, that's our plan. When you do the math, you should get 135 kilojoules released. Questions here? That's it for chapter 7. Very big chapter. Lots of math. But practice and you'll be fine. I will have office hours next week. So that's Tuesday from 11:30 to 1. If you need some help with your homework, you have some questions, you can roll on through. You have Mastering Chemistry due on the 31st. That's Wednesday of next week for Chapter 7. Just to let you know, you also have your next exam, and that covers Chapter 7 and 8. We're covering Chapter 8 in class next week. And it's been a struggle because we had 2 classes that we missed, which put us behind schedule. The video for Chapter 8 is already up. It's been up. You'll also notice that there is an assignment there. There's a Chapter 8 check-in. It's not due for a couple of weeks, so you don't have to think about it. But in preparation for class next week, please, please, please watch the Chapter 8 video. Be prepared to do practice problems so that we can roll in exam review and covering all the Chapter 8 concepts. So we'll start off with doing some Chapter 7 review, and then we'll continue doing review, but we'll cover all of the points of Chapter 8 using kind of exam review and some other examples. So please watch that video, take some notes, and be prepared, because we're not going to step through every single gas law. Chapter 8 is on gases. We're not going to step through and explain every single one. And I see screen sharing said, we're just going to disconnect. But it's all right, because we're done with class. So if you have any questions, we have a couple of